Okay, I think we can start today's lecture. A reminder about the submission of writing assignment 1, which is due this Wednesday at 11:50 p.m. Midnight. And the writing assignment description is the second link in the writing module in the Canvas. Please submit with a submission portal under week 4. And if you have any questions, you can ask either by sending email or by chat, okay? Today, this lecture is about inverse of Laplace transform and partial fraction expansion regarding real roots and complex roots, which are the first 2 cases of partial fraction expansion. Sorry. So remember, given ordinary differential equation, there are 3 steps that we use Laplace transform to solve the equation. First is to take the Laplace transform, which is to transform the ODE from the time domain ft into the Laplace domain fs, which is also the frequency domain. And then we can use algebra to solve for fs. And in the end, we can take the inverse transform, which is to transform the Laplace domain solution fs back to the time domain to find ft. And fs can be expanded to be fs equals f1s plus f2s all the way to fns. And if Laplace of each term exists, then we can simply write the inverse Laplace as the summation of the inverse Laplace of each of these parts. And in the end, we can get ft equals f1t times f2t all the way to fnt. And this leads to the partial fraction expansion technique, which we talk about one of the forms, fs equals bs over as, where we have a's as the numerators of partial fractions, and p's are the poles. Roots are negative values of the poles of as, and we need to find all a's and p's, and then we can invert each partial fraction term to get the in the end to get the time domain solution. And to find the roots using we can use MATLAB. Here we have an example. Given s cubed minus 57 times s squared plus 875s minus 3675 equals 0. We can type the following command in MATLAB, which is roots. Here we use a bracket. Inside, we can see are the parameters for the s to the power terms. First is 1, which is the parameter, the coefficient for s cubed, and minus 57, which is the coefficient for s squared. And in the end, it returns 3 roots. Root 1 is 35, root 2, 15, and root 3, 7. And then we know that this polynomial form can be written as s minus 35 times s minus 15 times s minus 7. And there are several cases when we do partial fraction expansion. First is distinct real roots, which means all the roots are decimal values, either positive or negative. And we can also have complex roots, which include I or j, depending on the notation, which is the square root of -1. And then so we always have a pair of complex roots if we have complex root, which is s equals a plus ik and is conjugate s star, which equals a minus I times k. The third case is repeated roots, which will be covered in lecture 7, which is Wednesday's lecture. And these are all recognizable in the Laplace table in the course packet. And for case 1, with distinct real roots, the numerator power is less than the denominator power, and the roots are minus p1, minus p2, all the way to minus pn. which are the negative of the poles and are real. And there's no I term, which is the square root of -1. There's no I term. And so for this case, Fs can be written as this, which is just shown in the previous slide, where A1, A2, A3 to AN are the coefficients, and we need to find all A's and P's in this case. We can use MATLAB by writing the Fs to the form as Bs over As equals polynomial for Bs over polynomial for As. We can use the MATLAB command residue with two inputs, first input Q and second input G. As we can see, Q are the coefficients of numerator polynomial for Bs, and G are the coefficients of the denominator polynomial As. And the second case is complex roots, which means it contains the I part. And there are two forms. First form is the polynomial itself. Second form is the form that we can use to find the complex roots, which is s plus a squared plus k squared. And the second form can be found in the Laplace transform table, column 3. And in this specific case, we can refer it to equation 25 and 26. And then we can use MATLAB residue command to find the roots. Here we use ARK, the output, equals residue with input 212 and 125. 212 and 125, these are the parameters for the polynomials of numerator and denominator. And after we run this command, we get returns with A's and R's. A's are, both are complex number here. And in the end, we can write Fs with these A's and R's, which is 1 minus 2.5i over s minus -1 plus 2i plus 1 plus 2.5i over s minus -1 minus 2i. And then we can reorganize the denominators and get this a new equation for Fs. Is this in the form to take inverse though? And if yes, which equations? In fact, we need to reorganize again to get this, hold on. And this is the time domain expression after we use the inverse Laplace transform. And we can go on and write the e to the power 2it and e to the power -2it into the cosine and sine form, which is called the Euler identity. And in the end, after we expand the e power term into an sine form, we can get the final solution of ft, which is e to the power -t times 2 times cosine 2t plus 5 times sine 2t. And the example is shown in page 6.3. And now, if you don't have any extra questions, we can work in groups for class activities, and you can discuss and ask questions by raising your hand. And in the end, each of you will submit the class activity in the Canvas submission portal. So any questions? Stop share. All right, Joe, free online implementation of MATLAB. Okay.
So are we using MATLAB for every problem or only the ones that specifically ask for it?
You can feel free to use MATLAB when you think it's possible. Let's say it that way. Okay.
Okay.
And Joe suggested a free online implementation of MATLAB. And there is also another way of using MATLAB, which is the cloud version. here at the University of Minnesota called Apps2Go. So if you install Citrix, which is just like another user interface compared to your Windows system or your Mac system. And there you can see the available software for you to use. Most of us should have access to MATLAB